have to watch
I just ignore the awkward, first 15 seconds of the video or so if you decide to take a look at this video. So there are several people in this class that are on the soccer team, and they are currently in Alabama, so I'm recording the lectures. Thank you. It's for them. There's applause in case you can't hear it on the video. And so I'm recording the lectures from today and on Thursday for them, so keep that in mind if you want to, share something with the class as a whole during our lecture breaks, and you don't want your voice to appear on this, don't share too loudly. Some other reminders of what's to come. Next week on Tuesday, our exam 4 will open up. It'll open up Tuesday at midnight. We'll be open all day Tuesday, all day Wednesday, all day Thursday, at which point it will close. And so I should have the study guide up today, and there will not be an opportunity to do the, extra assignment with this one, the study guide. And then pretty soon, probably next week at this time, I will get you the study guide out for the final exam, which will be cumulative. As a reminder, y'all decided as a group to not eliminate the final exam and move exam 4 to finals week, but instead keep exam 4, keep the final, and drop whichever of the 5 scores is lowest, which could include the final exam. As of right now, we have not had everybody in the class complete the Kafe, meaning we cannot replace your second lowest exam score with your highest in addition to dropping the lowest as of yet. The last time I checked, we had 22 of the 40 people complete the Kafe, which is actually pretty good at this point. Let's see. Any other announcements? Oh, yeah. So I didn't get the videos done again before I came here, so we're going to have the awkward transitions as I close things down, mute the screen, and then switch over to YouTube, wait out the advertisement, get the screen back unmuted. Bless you. And because that was really annoying to me, just practicing it in my office, I only have 2 videos today instead of 1 for each framing question because the transition bothered me. And I'm sorry. But it's my fault. It's not your fault. I don't want you to feel guilty or anything. Just it's my fault, and you can hate me. That's fine. The list of people who hate me gets longer and longer every semester. It's kind of an interesting thing that happens. I think that's it as far as announcements. Unless, do y'all have any questions? Things I've forgotten to talk about? Yeah.
Is chapter 28 going to be on the last exam?
Chapter 28. No, it will not be on exam 4. It will be on the final exam. Yep. Yeah, that's a good question. Yeah, this week we're doing chapter 25, at least the first 4 sections of chapter 25 and chapter 27. So today we're going to get through chapter 25, at least the first 4 sections on the urinary system, and then on Thursday we'll talk about the reproductive system. Yeah.
So will we get the opportunity to make a big study guide thing for these?
For the final, possibly, not for exam 4. Yeah. I mean, you can do it, absolutely, but there is not going to be an assignment on Canvas for it. Yeah. Any other questions? This is fun. Interaction. Nothing? There are a lot of people here. I've forgotten how many people are actually in this class. I'd say besides the soccer team, we're pretty close to everybody who's registered for this class, which is awesome. It's a great way to welcome me back from Thanksgiving. Thank you for that. I'm sorry that I didn't post any videos like I told you I was going to. My wife said that was stupid and not to do it. And so I said, it is stupid, but I still want to do it. And then she gave me a look that let me know that I really shouldn't do it, so I didn't do it. I think it's just she didn't want me sitting and uploading something when I should be helping to take care of the children, which makes sense, because there are a lot of them. Now I think that's it. Does somebody want to pray for us as we get started? I'll pray. Father, thank you so much for just what you do in our lives. I know that in the midst of this time of the semester, things are hard. It's hard just to get up in the morning and to go to the classes that you're supposed to go to. And Father, I just pray that you would give us strength and direction and wisdom. And Father, don't allow our time management to become just a game of putting out fires, but instead help us to be diligent and wise and really manage all of our responsibilities well, that we can excel in everything that we do and we can prepare fully for all of our tasks. Father, I ask these things in the name of Jesus. Amen. All right. So again, today we're going to talk through chapter 25, at least the first 4 sections, and I whittled that down to 5 framing questions. 5 framing questions for us to deal with, us to talk about, and hopefully through that give you at least a general sense of the big picture of the urinary system. Hopefully in lab, as you do a urinalysis, is he going to have you do that this year, or have you already done that, where you pee in a cup and do a urinalysis? He's done it in previous years. I hope he does it again this year because it's fun. Maybe he does that in physiology and not in anatomy. He doesn't do it in physiology? Oh. I hope that happens. That's kind of fun. But combined with what you get in lab, you should have a pretty decent understanding of what's in the urinary system, why it's in there, what it does, and overall what the urinary system does, which hopefully by this point in your life, you've got a good sense of the big picture of what the urinary system does. All right, so first question. What are the components of urine? And how could you use them to diagnose an illness or disease? Now, this was a section, the first section of chapter 25, where the text just says the composition of urine changes under a number of different conditions, which is true, but it's not really very helpful to not give you kind of a baseline of, what's in there. It gives you a nice table where it shows, okay, well, this, urine is typically odorless. Urine typically has a pH range of this, and you're like, oh, wow, well, that's cool, but what's in it? And so I pulled some additional information for you as a gift to you. I know it's not December yet, but it's after Thanksgiving, so it's Christmas time. How does the urinary system differ between males and females? Talk about that. What causes urination? That'll be a fun slide for us, for me. How does the gross anatomy and the location of the kidney dictate its function? And then finally, how does the microscopic anatomy of the kidney help us understand its function? All right, first one. What are the components of urine and how could you use them to diagnose an illness or disease? That is, use those components, the proportions of those. All right. Talk a little bit about what the kidneys do. So in case you did not know, the kidneys filter out particles. They filter out metabolic waste. They filter out toxins. They basically filter out anything that's in the blood that ought not to be there. Okay. And so that's what the kidneys are doing. And they filter out particles mainly based on size. Now, when you get into other aspects of those particles, like are they charged? Are they not charged? Are they polar? Are they non-polar? That impacts how another function that happens in the kidneys work, but not so much the filtration. Filtration is mainly based on size. And so because the kidneys filter based on size, large material should not be in the urine. The urine should not contain cells. It should not contain large proteins. It should not contain complex carbohydrates. Anything that's really big shouldn't be in there, because it should not be able to actually get into where all that has happened. That's not to say it doesn't ever end up there, but it shouldn't. Also, most of the ions in the blood, so as the blood is being filtered, most of the ions have to be reabsorbed. They're there for a reason. They're there to help your body maintain homeostasis. They're there to maintain water balance, and so they're essential. They're useful and needed. And so most of those get reabsorbed. That's the other function of the kidney. So one of the function is filtration. The other function is reabsorption. And reabsorption, the materials that get reabsorbed do have a great deal to do with, their polarity or their charge. You'll talk a lot more about that in physiology. You'll get your fill. You'll love it. Maybe you won't. I don't know. All right. Now, this is a statement right out of the textbook. under the section of composition of urine. And it just says the composition of urine varies. And it's like, wow, that's awesome. Thank you for that. But how does it vary, and what should we expect to find? But it does vary depending on your diet, depending on your level of exercise, your level of physical fitness. Varies based on environmental conditions, and varies based on your stress levels. And that's where it leaves it. And I didn't like that, so I brought in some additional information. So these are the typical components of urine. Besides water. Water is the main component of urine. The water composition of urine is as high as 99%. It can be as low as 90%, but it makes up the overwhelming majority of the volume of urine. Besides water, here's what you typically find. Urea. Urea is typically the next largest component besides water. Usually somewhere around 9 grams per liter. 9 grams per liter. And that may not mean much to you, but it means something to your urine. The next highest component is chloride, which is a chlorine ion. And this is an important one. This is one that's really essential for maintaining water balance. Water tends to follow chloride as you're moving chloride around. And so chloride is a big one. It needs to be reabsorbed, but we have a lot of it. And a lot of it ends up in the urine. The next highest component, sodium. And then, so these are 3 components that you almost find in every collection of urine. Another common one, but you don't find in every collection, is potassium ions. And then another one that you don't find in every sample, but you often find it, creatinine. And then from there, it gets into really trace amounts that you rarely find. All right. So those are the components of urine. That's the first part of this question. And then the second part of the question, how can we use these components to diagnose an illness or a disease? And this is where we don't necessarily use the typical components of urine, but we use the things that shouldn't be there. Okay? So an example of that, excessive white blood cells in the urine indicates some kind of an infection. Usually the highest suspect area is that it's some kind of a urinary tract infection if you have a great deal of white blood cells in the urine. But if you've got a heavy infection anywhere in your body, you're going to find white blood cells in your urine. Excessive glucose in the urine indicates diabetes mellitus or mellitus. And so what they used to use to diagnose diabetes was to taste your urine. And if your urine was sweet or tasted a little bit like that, then it was an indication that you had diabetes. Hopefully they made you taste your own urine, right, as like a consequence of developing diabetes. Right? This is fun. I tried to find some videos, so I wanted to go with this to do a urine prank. And the videos were either not in English, which was unfortunate because it was funny. It's a doctor walking around with a water bottle full of what looked like urine, I'm assuming asking people to drink it, but I couldn't understand the language. So I didn't know for sure what he was asking. And then the other urine pranks, I mean, there's just a lot of interesting language. Yeah, I couldn't really use one of those. But anyways, we'll talk a little bit more about our video in a little bit. So, any questions about the typical components of urine or how you use some unusual components to diagnose illness or disease? Okay, so let's do our first lecture break. What I'd like you to do is get yourself into a group of 6/7/8 individuals. And some of you may have never experienced one of these, but I think everybody probably has. I mean, I don't know what to do with this number of people here. I don't know if we should just stop what we're doing and have ourselves a little celebration, right? Have ourselves a little feast, but I'm ill prepared. I didn't bring any food. So, but if you could get yourselves into a group of 6/7/8 individuals, elect yourself a discussion leader, and then the discussion leader, your job is to get everybody engaged. Every voice gets heard, and get yourselves a representative. Oh, yes. I do remember now. 6/7/8. If you have trouble counting, ask for help.
It's just us right here. They're not with us. Say no.
Are you and Brooke by yourselves, Josh? Oh, you're with this group up here? Okay. Alrighty. So are you all in a group of 6/7/8 that you're at least remotely okay with being a part of? Okay. Do y'all have a discussion leader? And remember, discussion leader, your responsibility is to get everybody engaged and to find yourselves a representative. All right. Here's our first lecture break question. Why is it important for the composition of urine to change in response to environmental conditions? So in response to diet, that makes sense. If you're eating things you ought not to, you got to get those out of your blood, right? Or if you're eating a high protein diet, you're going to have a lot of certain types of metabolic waste, and you got to get rid of those metabolic wastes. But why is it important for the composition of urine to change in response to environmental conditions? So not to change in response to what you're putting into your body, but in response to what your body is being exposed to. All right? Take, 2 minutes and work some of this out. It might help if you focus on a specific environmental condition rather than just very generally. Maybe deal with, like, if temperatures get really high, why is it important for the composition of your urine to change? If temperatures get really low, why is it important for the composition of your urine to change? All right? Take a couple of minutes, starting now.
What happens when it's like super humid? Well, I mean, it depends on the temperature outside. Like, if it's really hot, so if it's really hot, what happens? Your urine gets darker, and then if it's cold, and it's cold, it might. I mean, it's like lately it's been like a lot less.
It can be 69 degrees outside and have 80% humidity and still lose a lot of water because that's no active.
Okay, so what benefit do we gain? Wait, you're in a discussion. You talk. Okay, so then you speak first. Okay, so what benefit do we get from?
Oh, thank you.
It was just hanging there. It was messing up. I think it's like a benefit of what's actually going on inside. It's just like
I think it's important.
just a product of like. So it's like actually adapting. So it's like in a sense we're like absorbing the it's just different. So we're taking in different things because of the environment, and it's just.
Or as it's losing it because of
So it's just
It's just darker because of like whatever we're taking.
So outside changes the inside. Whatever. I don't know how to put this into words, but we got an idea.
You have to be
Our boss. So what are you gonna say?
All right, 10 seconds. Wrap up your thoughts. Get a representative if you don't already have one. Bless you.
You want to have,
Yep.
it's hot outside, there's going to be less variety in your urine.
All righty. We're going to start here, and we're going to do ourselves a little counterclockwise circle. All right? So we're going to start here. What are some reasons why the composition of our urine has to change in response to environmental conditions?
when you're in trouble.
No, please.
I'm sorry. Okay. Mauricio brought up a good point with the movie Castaway.
Okay.
Saying that like when the character was in a position where he didn't have a lot of access to food or access to a lot of water,
Yep.
his body would slow down.
Yep.
A lot, and so that could be something that could be a way that your body responds to environmental conditions if it doesn't have access to fill in the blank.
Absolutely.
It'll slow down.
Yeah, metabolic rate changes a great deal in response to environmental conditions, at least in humans. We have a very, what you call a thermoneutral zone, Ours is very narrow, and what that represents is the range of temperatures at which your metabolic rate remains constant. Ours is very narrow. It's somewhere from, I think it's anywhere from like 25 to 35 degrees Celsius, which is about, I don't want to do the math right now in my head to figure out what that is in Fahrenheit. It'd be somewhere like 75 to 95, somewhere in there. And so, I know I said I didn't want to do the math and then I did it, but somewhere in that range. Anything outside of that range, our metabolic rate changes. If your metabolic rate changes, you're producing fewer and different types of metabolic waste. And in response to that, your urine has to actually make up for that. You know, with your pun, it reminded me of something. So I used to do like the Walk for Life when I was in high school. And there was a urology clinic in the Antelope Valley where I lived that would always show up to the walkathon, the cancer walk, and they always had a big banner that said "Urine Luck," and then had a cup of urine on their banner, and then talked about how they're gonna help you if you get any type of urinary tract issue. So, but I remember that very vividly. Not just the urine luck, but then that big picture of urine on their banner. It was not a very pretty picture, but it's stuck in my mind, and I think that was their point. Yeah. What do we have back there?
Our group, we just talked about how when temperatures increase and you start to perspire more, you can need to drink more water.
You do. Yeah, absolutely. So evaporative cooling is really, really important to keep our bodies from overheating. And in order for evaporative cooling to work, you have to have water to spare. And so, yeah, your kidneys have to reabsorb a great deal of water. Now, they already do. Typically, the kidneys retain like 80 to 90% of the amount of water that initially enters into the kidneys during the filtration process. That's just to maintain water balance. But then when you add to the fact that you have to now use water for evaporative cooling, that percentage goes up. And so the concentration of your urine goes up as well as you start using less and less water in it. All right, what do we have back here?
So we talked a lot about how just the levels of liquids in your body help maintain that homeostasis.
Yes.
With your temperature and stuff. And so with that, if you're in like a hotter climate, you need more of that to maintain that level. So it can't be being expelled from the body.
Right.
And so those levels are going to fluctuate to help maintain that level.
Yeah, I mean, our bodies are mostly water by mass, and basically every reaction that happens in our body takes place in water. So it's not just retaining the water for evaporative cooling, but it's also retaining the water for those chemical reactions necessary to maintain homeostasis. Love it. What do we have here?
We kind of said a similar thing about in a hot environment there'll be less water fluid in the urine and more concentration of ions and
Okay.
components.
Yeah. What do we have here?
So we had said that when like temperatures are rising, your body is gonna separate the ions differently.
Uh-huh.
So like you might have less chloride, for example, in your
Okay.
bloodstream.
Okay. You know what's really cool is it's actually not really cool. It's really sad. But we're not. It's actually not that sad. We're not designed well to live in water, right? That kind of makes sense. We don't live in water. We're not aquatic organisms. So we're not really designed well to live in water. Because of that, whether you go in fresh water or seawater, you've got a huge issue in that we have very little ability to control the flow of ions. So if you get into fresh water and you're in water where it has less stuff in it than the water in your body, we lose a lot of our ions. And the opposite happens in marine water when there's more stuff in the marine water than there is in the water in our tissues, and we absorb a lot of ions. So that's another area in kind of extreme environmental conditions where the composition of our urine has to change a great deal. If you were, say, stranded at sea, kind of hanging out in water waiting for somebody to come and get you, your urine would have a much higher ion concentration than it would typically, because you're absorbing ions out of the seawater and you have excess ions that need to be ridded with the urine. All right. So here's a nice figure from the text showing urine color. with response to the amount of water that you have at your disposal. Yeah.
A lot of points in the discussion lecture break thing involved the body in response to warm temperatures.
Yes.
What happens? Is there like anything that happens in response to cooler temperatures that would be different?
Yeah, so when the temperatures are under 25 degrees Celsius, your metabolic rate increases. Okay? Your muscles start contracting a lot more. You just start breaking down a lot of your energy stores. And so you start producing a lot more metabolic waste. So when the environmental temperatures are below 25 degrees Celsius, somewhere around 75 degrees Fahrenheit, you start producing a lot more metabolic waste. And so the concentration of your urine also increases. But it's not because you're putting less water into it, like it is when the temperatures are high. It's because you're filtering out more metabolic waste. Yeah. Did you have something, Dana? The same question. Look at that. All right. So here is our awkward transition. I don't like this either. That's why
I'm getting low on water.
Okay, so there's a lot of question of what to do during these lecture breaks, and it's like, okay, if you can't do a urine prank, what's the next best thing? And so we find Bear Grylls drinking his urine.
And the only thing I can do is to drink my own pee. And this is
Absolutely only
something I've never done before. And I'm expecting it to be pretty horrible. But I need to keep those fluids going in. It may seem disgusting, but your own urine is safe to drink. And if I just peed on the ground, that's all those fluids wasted. God, there's no getting away from it. That really is pretty horrible. It's like warm and it's salty and not my favourite. But I've got about a quarter of a bottle now for later as well.
Just a last little sip, just to make sure it was.
It's so gross. This is really not that.
There we go. And we're back. What's that?
Does your metabolic rate go up when in increase in temperature and decrease?
No, your metabolic rate slows in response to an increase in temperature, usually. Although it can increase under stress if you're, it depends on how your body responds. Oftentimes it responds by slowing the metabolic rate because that's how we produce an enormous amount of heat. All right, so how does the urinary system differ between males and females? Well, both systems have the same features. Two kidneys, usually. Two ureters, usually, draining fluid from the kidneys and taking it to a single bladder, a bladder with what's called transitional epithelium. Epithelial tissue that's not found anywhere else in the body. A special type of epithelial tissue. And then through a single urethra. So these are the components of the urinary systems in both males and females. Two kidneys, two ureters, a single bladder with a special type of epithelial tissue, and a single urethra. Now let's talk a little bit about the differences. The urethra of males is much longer than the urethra of females. And so that does have some implications as far as the function of the urinary system, but not many. Where it really comes into play is the frequency of urinary tract infections. So because the urethra of males is a lot longer than it is in females, bacteria or any contaminants would have to move a long way to get to the bladder. And so urinary tract infections are much less common in males than they are in females. And there's another nice factor about having, two separate places, the ureters and the urethra, where urine is carried in a duct. Well, it's actually not urine until it gets to the bladder, but where it's carried in a duct, and rather than sitting in a big reservoir and having long pathways. And it just really makes it to where if something was going to move from the outside all the way to the kidneys, it would take a really, really long time. Okay, it makes it very unlikely because a kidney infection can easily become fatal. And so bladder infections, relatively easy to treat, relatively common even in males, but much more common in females. Kidney infections are rare, but are much, much more dangerous than bladder infections are. All right. So our next lecture break question. Why is the lining of the bladder unique? So if this is the only place in the body that we find this unique type of epithelial tissue, why is that? Why is that necessary? And don't go just with, well, the bladder needs to expand. Okay? Yes, that's true, and that's part of it. But come up with some other ideas as well. I'll give you a couple of minutes talking about this among the members of your group. Discussion leaders try to get everybody engaged, and then we'll talk about this collectively. So why is the lining of the bladder unique?
So I was thinking,
Not only that, the bladder has like transitional epithelium. The book was saying like it has something where it goes from pseudostratified epithelium cells to choroidal cells. So like as it's expanding, it changes the type of cells that it uses for the bladder. It's like a line. So the farther out. Share. That was super interesting. This is information on
I know,
a daily basis.
I'm trying to like go back. I'm trying to go back to why those are important.
So the cells are farther out in the bladder. So in the outer layers, the cells change. The lining.
Yeah, I like it. Yeah, I noticed when you do like your beach, Not my fave.
Are you sick too?
Yep.
Okay, I've got it.
Yeah, I'm trying to find Yeah, there is a gap.
All right, so now we're going to go in the opposite direction. We're going to start up here and we're going to move clockwise and finish up over here. Do y'all need some more time? Okay, they need some more time. So we'll give 20 more seconds. Is that enough? 30 more seconds. 30.
Oh, it seemed like the transition epithelium inside the bladder, so like the lines of bladder as it expands, it changes the shape of the cells.
That makes sense, yeah.
So it goes from pseudostratified to like a boil, or no, pseudocolon.
is that because it's stretching or is it?
Well, because of the stretching, it changes.
What about the lining? Why is it that way? Does it prevent reinfection of virus?
Well, the question is, why is the line? That's something that's, I don't feel like he's gonna tell me.
Okay, Christian, you're answering that.
All right, so now we're going to start up here. We'll move clockwise and make our way around the room. What do we got from up here?
I was saying, like, as the bladder is becoming filled, it actually changes shape as it expands, like from a columnar shape, stratified columnar shape, to like a cuboidal shape.
Yeah, the shape of the epithelial cells.
Yeah, so the lining itself also changes.
Sure.
As it's expanding.
Yeah.
So that's what I was getting at.
Okay, so that the nature of the tissue themselves, having that transitional tissue, allows the wall to even change as it expands. That's good. I like it.
Oh, yeah. It needs to be strong enough to contain all the metabolic waste that the urine has, and well, acidity. So it has to be strong enough so it will diffuse through the lining.
Sure. Yeah. So urine doesn't start leaking out. What do we have back here?
We talked about how it protects against infection with all the foreign material inside, and also it allows the urine to pass through the urethra more smoothly.
Okay. What do we have back here?
We talked about that. It's not like whatever's in there is going to stay in there. It's not like the intestines. What they take if they
Sure, there's not a great deal of absorption for sure.
lining in there is a lot thicker. Probably present inside there.
Yeah, and so part of it is just it's functionally different, right? A lot of the epithelial lining, there are other places where the epithelium is just a barrier, but it's done in a different way. This is a barrier that also needs to stretch, and that's very unique. That's a unique need. It's not just needing to stretch, which that is wonderful that our bladders can stretch, but it also needs to provide an incredible barrier against infection. Yeah. What do you have up here?
They also said the same thing in terms of the tissue preventing the bladder from tearing.
Okay.
Because that would be very bad.
Yeah, it would. Yeah, and it's not just about stretching. It's also you don't want it rebound. You don't want it to be as elastic as some other epithelial tissue. You don't want it just, applying pressure to shrink back down. Although it does do that, and there is some of that. But yeah, and we'll talk more about this in the next slide. But the total volume of fluid that the urine can hold easily can reach 600 milliliters, which is over half a liter. And for some people, you can train your bladder. You could increase the strength of your external urinary sphincter, and you can actually get your bladder to regularly hold a liter or more, which is awesome to have something that can stretch that much. That's dangerous. But anyways, all right. So here's the structure of the urinary system. Here are the two ureters that connect the kidneys to the bladder. Here's the wall of the bladder and the single urethra that drains the bladder and deposits the urine outside of the body. Here's a figure showing you the difference in length of the female urethra compared to the male urethra. Here's the female urethra compared to the male urethra. And so the increase in length makes it a lot less likely that bacteria can penetrate all the way to the bladder. Awkward transition. This one I needed to maintain too because I wanted to show you all a video of Bear Grylls drinking his own urine. And then I had to show you my next favorite urine moment on screen. How's it going? Have a good break?
It's not too late to save at Samsung.com.
Well, I guess that's it. It's okay, everybody, back on the bus. Hey, what's with Ernie?
I don't know. I'll be right back. Hey, Ernie. What's up?
Nothing.
You falling in love with the wall or something?
I had an accident.
You had an accident? What does that mean? You! Oh, I know. Okay. Don't worry, buddy. You hang tight. I'll be right back.
Of course I peed my pants. Everybody my age pees their pants. It's the coolest.
Really?
Yes, you ain't cool unless you pee your pants.
Wow. Hey man, Ernie pees pants too. All right.
I know, that was sweet.
If peeing your pants is cool, consider me Miles Davis.
Oh, that was the grossest thing I've ever heard in my life. Let's go. Get on the bus here. Move it. Get up there. Dial 1257. Move it or lose it. Get on the bus. Hi, Miss Vaughn. Nice to see you.
All right. Our third framing question. What causes urination? What causes urination? So micturition is the process of voiding the urine. It's the technical term for urination, and it's under both voluntary and involuntary control. Usually it's only small children that experience the involuntary control. So that should say there. There is both an internal and an external urinary sphincter. So there is both, not the is both. So when the urine volume reaches about 150 milliliters, which isn't all that much fluid, the internal sphincter relaxes. The part that's under involuntary control tells your body it's time to empty the bladder. It's time to empty the bladder. For most people, that's about 25% capacity. About 25% of what your bladder is capable of holding. Your body tells, basically, your central nervous system tells the internal urinary sphincter to relax, and that's when you first notice the feeling of needing to urinate. Now, we also exert voluntary control on the external urinary sphincter. So we can choose to keep that muscle contracted, the external urinary sphincter, and to keep from voiding the urine. So as you develop, as an infant develops, and as a toddler develops, these muscles in the abdomen get stronger and stronger and do a better job of keeping that external sphincter closed. But muscles in the abdomen can then relax that external urinary sphincter and allow the urine to be voided. And so, yeah, this is a process, and it's important that it's under voluntary and involuntary control, because early in development, your muscles are not strong enough to actually control the process. And so it's helpful that your body can empty the bladder on its own. As you get older, that is no longer important. It's no longer an important factor to be able to get it to happen on its own, although under certain conditions it can become basically impossible to relax the external urinary sphincter, and so the only way to void the urine is using a catheter. All right. I have a lecture break question on this one, but I don't want to do it. So we'll move to our fourth framing question, and we'll do our lecture break here. So how does the gross anatomy and location of the kidney dictate its function? How does the gross anatomy and location of the kidney dictate its function? If you remember from the first week of this class, when I think virtually everybody in the class was here, I counted we're at 31 of 40, but I think we have 5 people gone in Alabama. So, yeah, we're at a pretty good percentage. But gross anatomy, this is the large scale anatomy. This is the anatomy you can see with the naked eye. And so what we want to talk about is how does the gross anatomy of the kidney and where it's located dictate its function. And so first of all, you have to know that the kidney is actually anchored behind the peritoneum. It's what's called retroperitoneal. And so most of your organs sit inside of your abdominal cavity and are surrounded by a tissue layer called the peritoneum. The kidney is not. It sits behind this. The ureters also sit behind the peritoneum, and part of the bladder sits behind the peritoneum. And so with that, it doesn't have as much of that fluid protection that some of the other structures have inside of the abdominal cavity. But it is buried under fat pads and partially protected by the ribs. And so its location helps to provide some protection, not necessarily to dictate its function. So the kidney divided into two regions. When you look at the kidney, if you cut it open, you can see these two regions very easily. You've got the peripheral rim called the cortex, and then you have the medulla. And I'll show you an image of the kidney where you can see both of those structures. And so what you look at, or what you see when you open up the kidney, is you see a great deal of open space where fluid drains and pools and then moves into the ureters. And then you see a great deal of tissue where the two functions of the kidneys are happening. And what are those two functions again? Filtration, reabsorption. Okay, you can see those where they would happen. Now, each kidney contains about 1.3 million nephrons, and you can't see these nephrons. They're not part of the gross anatomy, but you can see where they are on the gross anatomy of the kidneys. You can see where they're located. So I wanted to introduce them here, and then we'll talk about them more in our last framing question, which addresses the microscopic anatomy of the kidneys. So within the nephron, you have a capillary bed. You actually have two capillary beds. You have a structure called the glomerulus, and this is the main structure associated with filtering. So water is pushed through the glomeruli, which would be the plural form of this, and large materials, large proteins, cells, complex carbohydrates, material that's in the blood that's too big to move through that does not move through into the nephron and gets filtered by the glomerulus. Water drains through the glomerulus into what's called Bowman's capsule, and now you have this fluid that has some material that needs to be reabsorbed. A lot of what needs to be reabsorbed is the water making up that fluid, but we also need to reabsorb ions and reabsorb some other really essential parts that are inside of that fluid, inside of that filtrate. Now, some other gross structures of the kidneys. There are two capillary beds in what's called the renal portal system. So we talked about the hepatoportal system, not last week, because last week was Thanksgiving. And I think it was the week before, but may have actually been the week before that, when we talked about digestive anatomy. And what are some key aspects of the hepatoportal system? Where do you find it? What does it do? I know this isn't a typical lecture break, but I felt inspired to ask this question. Feel free to share. Hepatoportal system, where do you find it? What does that root hepato mean? Like hepatocyte, hepatic vein, hepatitis.
No, small intestine.
So this part, the actual portal system is in the liver, but it does drain the small intestine, right? Everything that gets absorbed in the small intestines passes through the liver for decontamination, right? To filter, to get rid of toxin, metabolize certain things that you do not want to into your bloodstream moving into your body, right? And so the hepatoportal system also has a capillary network to get those hepatocytes involved so that those materials that are being absorbed can be processed inside of liver cells, those hepatocytes. Okay, the hepatoportal system has a single capillary bed. The renal portal system has two capillary beds, where you've got one for the filtration and one for the other function of the kidneys, which is what? Reabsorption. And the nice thing about this is these capillaries are actually connected by a single artery. So it's not artery, arterioles, capillaries drained by venules. It's actually an artery that connects one capillary bed to another, keeping the blood under high pressure, keeping the blood, that's relatively highly oxygenated blood, but keeping things at a high pressure when that reabsorption takes place. So yeah, this allows for this process of reabsorption, the other process that takes place in the kidneys. All right, now here's our next lecture break question. What I want you to do is think through this, and some of you have examples that you can actually point out, but how is it possible for someone to live with a single kidney? Okay? How is it possible for someone to live with a single kidney, and what are some of the maybe pathologies you might think to be associated with somebody that's working with a single functional kidney instead of two? Take a couple of minutes, discuss this among your groups, and then we'll share it together.
I just assumed that they got one, so they just
All right, so we'll start here again, and we'll work our way counterclockwise. So think about it this way: if each kidney contains about 1.3 million neurons, that gives you 2.6 nephrons, not neurons, sorry, 1.3 million nephrons. Two kidneys give you about 2.6 million nephrons, an indication that the structures in the kidneys that are working to accomplish the task of the kidneys, the filtration and the reabsorption, are fairly important. And if you are to cut that number in half, how is it possible that somebody can function under those conditions? All right, what do we have? Some ideas?
So we said that the kidneys would have to work the same, and so one of them would just have to work twice as hard if you only had one.
Okay.
And then it might be susceptible to like more kidney infections or something, just because it's like exhausted.
Yeah, and so that's easy to assume, right? If you only have one, somebody's doing twice the task that they would have to do before. It's kind of interesting. What you find is under normal conditions, when you aren't putting your kidneys under incredible stress, you find that the kidneys aren't necessarily operating at max capacity all the time. There's some redundancy there to the design. Yeah.
I just have a quick question. If someone is in kidney failure and they receive a kidney transplant, so they really only have one kidney that functions properly, what happens to the other one?
I mean, it just deteriorates. Eventually it'll stop being fed. If it's not functioning correctly, eventually it'll stop being fed. A lot of the vasculature to it will just be redirected, and it'll just deteriorate.
So does it get like reabsorbed into the body, or does
Not really. I mean, sort of, but not really. Yeah. So like if you had somebody that functioned on a single kidney for 30 years, and you did an autopsy on them afterwards, you'll still find the non-functional kidney. It's not going to be gone.
You'll notice that you'll find that it was non-functional.
Oh yeah, you could tell that for sure. Yeah. All right. Some ideas back here.
We talked about how if only one
Yeah, good. What do we have over here?
We talked about there's a trade-off between quality versus quantity. You won't get the same quality of filtration with just one kidney.
Okay, potentially so. Yeah.
So we kind of talked about the same thing as like the body adjusting and how the body's pretty good at adapting to different changes. And but also like there are ways that an individual can assist that, and like that can be like being more careful with your diet and like just trying to be more cautious with your environment even, and trying to almost help your body out.
Yeah. All right. What do we have up here?
We kind of said the same thing, but also mentioned it might be a slower process,
Okay.
not so much.
Yeah, just the whole overall process is slower. Do any of you know somebody that functions with a single kidney? So you tend to do they have a modified diet? Yeah, diet not super high in protein, not super high in sodium. So yeah, you try to do your best to not tax the system. And what really taxes the system is protein metabolism and a lot of ions in the blood. And so having a diet low in sodium and having a diet that just has enough protein to basically allow you to function correctly and well is usually how we advise that. It also has to be taken into consideration when you choose certain medications to give to somebody, because the kidneys do a good job of filtering out the metabolic waste that comes about from digesting and metabolizing the drugs. And so you have to take that into account as well. But there is some redundancy. There's some redundancy in the design, and if you're operating normally and you don't have a diet that's way higher in protein than what's necessary, and you don't have a diet that's way higher in sodium than what's necessary, you don't tend to use both kidneys at full capacity anyways. Yeah.
This is a really random question, but why is the liver able to regenerate but no other?
Yeah, it's a good question. So the liver, because of the nature of the work that the hepatocytes do, that they're constantly exposed to really dangerous stuff, they die at a really high rate. And so the liver is designed in such a way that there are a lot of stem cells there to replace those liver cells that are constantly dying. And so that's the biggest thing about the liver regeneration, is the number of stem cells that you have inside of the structure. Yeah.
So, like,
Oh.
what happens in liver disease though? Is it just like too many cells are dying than what they can?
It depends on the disease, but yes, typically, yeah, that your death rate just far exceeds what you can replace. Yeah, and then obviously every stem cell you use is one less stem cell you have at your disposal. So eventually you run out, your reserve runs out. So dialysis can work in a couple of ways, but it basically works in the same way that your kidneys would. It's designed to take certain elements out without taking things out that would typically be reabsorbed. So it just runs your blood through something that's designed to pull out metabolic waste, designed to pull out certain ions that don't need to be there, but to keep others in. And so you don't get quite the same of the filtration reabsorption. You just get that getting rid of certain things that ought not to be there. Yeah. But it can be done in a number of different ways. All right. Yeah, you could actually run your blood over to like another animal and have their kidneys do the work for you, and then bring your blood back to you. And that actually works better than machine dialysis, but takes more time. It's a little complicated because then you have to keep something alive just for you to use. But you could do it with like pigs. Pigs, it works well to have pig kidneys filter your blood for you. So here's the kidney showing you partially protected by the ribs. And then here is the gross anatomy of the kidney. So here you can see the cortex, and then here you can see the medulla. And so you can see those two main structures of the kidneys, the peripheral cortex and the medulla, and your nephrons are basically lining this section here. And so then here you've got your renal pelvis, where that fluid enters after it's been filtered and reabsorption has taken place, moves through the ureters onto the bladder. All right, our last framing question. how does the microscopic anatomy of the kidney help us to understand its function? How does the microscopic anatomy of the kidney help us to understand its function? So again, talking about the nephron, consists of several structures. The renal corpuscle, or corpuscle, which this is the glomerulus along with Bowman's capsule. So where the water is forced out in the glomeruli and into Bowman's capsule. And then from there, water flows to what's called the proximal convoluted tubule. In the textbook, you see this mostly abbreviated as PCT. And inside of here, you have a filtration membrane where the basement membrane for that tissue of these cells in here that keep fluid moving fuses with the epithelial cell. So it makes it a really efficient filtration membrane where a lot of that reabsorption can take place, the filtration and the reabsorption. Then you have the loop of Henle, and here you get water reabsorption. Most of your ion reabsorption is done by the time the fluid reaches this point. And then the distal convoluted tubule, again, you've got some reabsorption happening here, but some dumping of extra materials. So a lot of your metabolic wastes enter here. Some of the larger materials that can't move through the glomeruli enter into here. All right. And so the last one of our lecture break questions, and this one is the most interesting one to me because it seems to be fairly counterintuitive. And here's the question: why do ions get pushed into the nephron just to be reabsorbed? Okay, so in the process of dumping material through the glomeruli, a lot of the ions that are in the blood get forced into the nephron, and most of those get reabsorbed. And so the question is, why do these ions get pushed into the nephron if they're just going to be reabsorbed? What is that? What is the purpose of that? And as you think through that, it would help to think through ideas of water balance. So go ahead and take a couple of minutes in your group and come up with some ideas of why these ions get pushed into the nephron just to be reabsorbed. Okay, a couple of minutes starting now.
Right, yeah, maybe it's something, yeah, some attribute. Maybe it's like something to do with the electrons. I have no idea. Jimmy.
Doesn't it like kind of save energy by making you go through the same process?
Maybe. All right, about 20 more seconds. Wrap up your ideas, figure out who's going to share them. All right. So we're going to start up here and we'll make our way around clockwise. So what are our ideas? We're going to start with y'all.
We're just guessing, but it has maybe something to do with osmolarity.
Okay? Explain that. What is osmolarity?
Well, it has a lot to do with what you were mentioning earlier, like when you're peeing in the ocean. And
You sure?
Maybe has more ions than what you have in
Yep.
your water, so then in the water inside of you, so maybe those ions will move into your body. That's just an example of maybe what's happening inside the nephron.
Sure, yeah. And so osmolarity is basically indirectly a measurement of which direction water is going to move. Okay? So osmolarity takes into account everything dissolved in the water, the total number of solutes. Okay? And so water is going to move from an area where there's higher water to where there's less water, which tends to be from where there is less solute to where there is greater solute. Okay? And so water is going to tend to move in a particular direction, and some of that you just are forced to keep solutes high in certain areas, even if some of those solutes are really essential, just to make sure water moves in the right direction. Okay? And a lot of times getting water to move in the right direction is so important that it's worth it to invest in reabsorption in order to ensure that water moves in the right direction and filtration takes place.
We kind of just talked about, we're guessing that maybe it has to do with recycling, just kind of trying to reuse the resources the body already has.
Yeah, I mean, absolutely. That's what you have a lot of in the blood are those ions, those essential ions. And so absolutely, it's a matter of using what is there to make sure water flows in the right direction. Yeah. Any ideas back here?
Kind of said the same thing, but added balances the ion level.
Okay.
Yeah, it was just to return the water and solute back to the bloodstream.
Okay. Return the water and solute back to the bloodstream. Good. Yeah, keep in mind, a lot of that water that enters into the nephron gets reabsorbed as well. So it's not just the ions that are getting reabsorbed, but also the water is getting reabsorbed. And so sometimes you have to do that just to force material that's not going to have a tendency to move and move with the water. You have some ideas here?
I was just thinking, do all of the ions get reabsorbed, or is there
Not all of them. Yeah, I mean, keep in mind that the second and third most common components in the urine are chloride ions and sodium ions.
So going with that, knowing that not all of them are reabsorbed, there still has to be some type of a filtration needed, which is why they would have to go through the nephrons, because not all of them are reabsorbed. Some of them
Absolutely. Yeah, and in the event that you have a really high concentration of a certain ion that you do need to get rid of a lot of, then it is really, really helpful that those ions are already moving in that direction. Like if you have a diet high in sodium and you need to rid your blood of sodium in your urine, it's helpful to have that process already happen. So here's an illustration of the two capillary beds in the nephron. Here's one here in the glomerulus, and then here's one around the proximal and distal convoluted tubules and the loop of Henle. And notice there again, these two capillary beds are connected by an artery and are not connected by a vein as you typically find in other portal systems. So I misspoke before when I said the hepatoportal system has a single capillary network. It has two, but it's a vein that connects the two capillary networks instead of an artery. And so here's where your filtration happens, and here's where your reabsorption happens. There is some filtration taking place, there is some reabsorption taking place here, but overwhelmingly, in this one, you've got your filtration. In this capillary network, you have your reabsorption. And so it's designed in such a way to accomplish that, to get material forced out, and then the essential elements to be reabsorbed and brought back into the blood. And so here's some more illustration of this filtration structure. The podocytes, where you've got this filtration membrane, and then the basement membrane from these podocytes fusing along with the epithelium, and just creating a structure that works really nicely for getting fluid to move across it. Okay, which is similar to what happens in capillaries, where you have a single cell thick, really, really conducive to fluid moving, but this is not built with just epithelial cells. This is also built with other cells that are designed to keep fluid moving, and so both those kind of fuse in a similar way to form a structure that's really conducive to allowing fluid to move, filtering what you need to, reabsorbing what you need to, keeping the urine flowing. All right? So that's it for our time. Enjoy the rest of your Tuesday. Be safe, and I'll see you on Thursday. We'll talk about reproductive anatomy.